Okay, let me begin. Thank you for the introduction. I'm Jonathan Huang. I'm a research scientist at Google. I do research on deep learning for structured image understanding, which is conveniently what I'll be talking about today. All right, it's kind of been a few years since deep learning has become popular in computer vision, and today we're starting to get very good at tasks like image tagging. For example, if I give this image to Google, it can pretty reliably tell me what's going to be inside that image. I might get tags like Obama, person, scale, right? That's very nice. And what's kind of been amazing is that over the last decade or so, almost decade or so, collectively as a machine learning community, we've lowered the error rate on the ImageNet classification challenge from about 28% top 5 accuracy to today it's 3%, hovering around 3%. So this is actually 2016. I should confess that as far as I know, it's still around 3% on ImageNet, but that's okay because we're actually now better than humans are at the ImageNet classification challenge. Which blows my mind a little bit, I would say. And the secret sauce has been deep learning. I'm not going to talk too much about kind of the specifics of ComNets. I'm sort of going to assume that people have seen this stuff, but if you have a question, please ask. And I really have nothing to show about these slides other than I think they're really nice visualizations that one of my colleagues made. Yeah, I think this is partly working. Okay. All right, so we've gotten very good at image tagging, and what's been really exciting over the last few years is that we've started to become a little bit more ambitious about what we can do in computer vision. Today, I would say that we are starting to have reliable technologies that can put boxes around objects in addition to classifying them. They can segment them, tell you what pixels belong to the object, and they can tell you a little bit about human pose, like what's the position of the skeleton, right, for that particular person. And so for these, I'm going to call them the core structured image understanding tasks. They're fundamental but somewhat complicated tasks that go beyond simple classification. And of course, it doesn't end here. So kind of in the future, we'd like to be even more ambitious. So we'd like to talk about things like attributes, like this person is laughing, and relations such as the fact that this person is standing or stepping on a scale. We'd like to know about the 3D layout of the scene. We'd like to know that it's indoors. Maybe even one day we can understand that this is supposed to be funny, because this is Barack Obama. He's this very high status former president of the United States, and he's stepping on a scale that one of his aides is on, and that makes the scale look like this guy is heavier than he actually is. It's not so funny when I explain it, but it's funny the first time you see it, right? So maybe one day we'll understand that. We're not there yet. And actually today I'm going to be talking about this middle slide. So again, okay. So just focusing primarily on this picture, trying to get that to be really good. I think what's really cool is that in the last few years, we've gone from, these things are just starting to work. And today, all of a sudden, we're seeing them in products. They're in our cell phones, right? And it's absolutely amazing. So I just want to give a tour of modern methods for doing these tasks. I think probably a lot of people have seen some of this already, but maybe not seen it kind of so close. So that's what I'm going to do. I'm going to cover 3 tasks: object detection, which is putting a bounding box around everything, segmentation, assigning labels to every pixel, and key point prediction, which is this task of essentially drawing a skeleton. Okay. All right. Okay, so that's today. Tomorrow, I'll kind of focus on more I would say, cutting edge research that's primarily my group is doing at Google. We're interested in kind of a few places where the current methods fall short. So dealing with video, temporal models, how to make things efficient. So how do you take a really good kind of high quality model and get to run on your cell phone is a really cool area of research. And finally, we'd like to spend a lot less money labeling data. So kind of one of the big areas of research is how do you learn with less supervision, or how do you make more from the data that you already have? Okay, so object detection, and actually what I should say is I'm going to focus 80% of today on object detection, partly because, so I lead the object detection team at Google, so I kind of know that the best, and the other sort of, once you know object detection, they sort of follow on fairly naturally. Okay, so object detection is used all over the place. Beyond Google, but I'll talk about some things that we have at Google. We use it to find faces in images. If anyone uses Google Photos, you'll notice that we detect, your baby's face, for example. We even detect your pet's face, your dog's face. We can cluster them together. That's object detection somewhere in there, right? If anyone has heard of Nest cameras, these are cameras that you can buy for example, for security in your home. And when someone comes up and knocks on your doorbell, we can tell, oh, there's someone there. And not only that, we can tell if it's someone who belongs to your family or someone you don't know, right? Here we're using it for shopping. You might be looking at an image, this image, for example, right? And it starts recognizing, oh, these are some of the products in the images that you're interested in. So we can find the handbags, and then we can, recommend some other handbags for you to look into. Okay, and we also use it in Google Street View. So if anyone's used Google Street View before, you'll recognize, this is not the best picture, but you'll recognize that when you look at the cars, the license plates are blurred out. And we're required by law to maintain the privacy of our, of these images. And so for every image on Google Street View, we're running some detector, seeing if there's a car, in the car if there's a license plate, and then just blurring those pixels out. And that's object detection. We even use detection to build the maps for Google Maps. So here we have cars that drive through every street, and every time it sees a supermarket or a Starbucks or whatever business storefront, it puts a little box around it and tries to classify that store. And of course, it's remembering where it is. And so now we know, oh, there's a Starbucks here in this map, and then there's a supermarket, an OXXO on this corner, right? That's very important for us. Okay. And finally, we even sell this technology kind of directly to other companies. So here's a company called Tryon that I don't know very well. And what it's doing here is, this just came out this week, I believe. So it lets you take a picture of a product, and then it finds out what it is. And then now you can manipulate that thing in 3D and maybe even try it out on your hand. And here, this is with another company who I don't remember, and we're tracking the cars from the traffic camera and trying to do some traffic analysis that way. Okay, so these are the fun pictures and videos, and now I'm going to talk about not so fun stuff, how it works, right? So what is object detection? I usually explain it as kind of the combined problems of classification and localization. So we need to know what it is and where it is, right? There are a few things that make this much more difficult than just standard ImageNet classification. So one is that I'm going to just keep track of the time. One is that we need to produce a variable number of outputs. So it could be that in this image we have 1, 2, 3, 4, 5, 6, 7, I don't know, like 8 to 9 people in this image. But in another image, there's 2 people. So somehow we need to handle this variable output setting. The other thing is often, and this is not obvious, often we have to classify based on much fewer pixels than the standard ImageNet setting. So here's one example. Okay, I'm going to show you this thing. And if I just showed you this thing by itself, you might not recognize what that thing is. But in the context of this image, most humans, especially if I tell you it's this guy over here, will be able to tell, oh, that's a person, and that person is actually holding onto a kite, right? And the reason why we can do that is because we're doing contextual reasoning. We're not only just looking at the pixel intensities of that one box, but we're looking around and seeing the larger scope of this image. Oh, okay, yeah. So, somehow we need to deal with these two things, and I'll tell you how. Here's kind of the outline of the object detection section. I'm going to start with something that sounds very classical. These are called sliding window detectors, and kind of move on to the modern era of doing detection with convnets. Talk about how to evaluate a detector. Detection metrics are a little bit harder to understand than typical kind of accuracy things that you might see in ImageNet. And so a big kind of a common question that I get online is, I know my detector gets blah, blah, blah on this data set. Now, what does that mean, right? So I'm going to tell you that. And then we'll just talk about some practical tips and tricks. If you want to go out and train your own detector, what do you need to do to get it to work well on your data set? Good. So here's the setup of sliding window detection. So if I tell you to invent how to do detection, invent an object detection algorithm for me, given that you already know how to do image classification, what would you do? All right? And the simplest thing that I think a lot of people would come up with is, let's just apply image classification at a bunch of kind of different locations in this image. So what we're going to do here is we're going to take kind of a small crop in this image, all right? And we are going to run our classifier. And our classifier in this case might say nothing. There's nothing there, nothing exciting there, all right? So we'll move over, and we will do the same thing. Our classifier will say, OK, there's nothing exciting here. And then we'll just keep on going, keep on going. And what's nice is, if I were a computer, I wouldn't get tired of this. But right now, I am getting tired, so I'm going to skip down here. And so you're going to slide across, and every time we're going to run a classification, and then every once in a while we might actually hit something. So here we're running our classifier, it's finding a person. Yay, we're very excited, and then we'll keep going, right? And so what's going on is every time I'm taking the pixels in that window, computing some features using my feature extractor f, right? F of this window, and then f of this other window of pixels. And that might be using a convnet, right? And then we just classify. So maybe we use a fully connected layer, could use an SVM, right? All right, so a few things to get this to actually work. So first of all, like I said, we often need context. So typically, we often put kind of a little bit of, we give it a little bit more padding, right? So instead of running our feature extractor just on this little kind of tight window on that person, we might give it a little bit of a larger window to work with. Okay, so that's how we incorporate our context. The other thing to think about is sliding window placement. So obviously we can't just, I'm saying obviously we can't just run a sliding window of that size and hope to detect everything. And so actually what we're going to do is slide. So there's a few options to do this. So we could be very slow, and the slow way is to just try everything, all right? And we'll slide over X and Y. We might have a stride, so it could be like, let's try something every pixel. That's very slow and very boring. And we also need to handle scale, so we might try windows of different sizes, right? We might try windows of different aspect ratios. So this is super slow, but probably the most accurate thing to do. The other thing you could do is be lazy and run it over a coarse grid, and and maybe not try this at every pixel, and that's probably okay too sometimes. And it's a lot faster. So the question is it really going to be that bad to do this? And it turns out what people now do is this thing called bounding box regression. So if it turns out that we tried a slightly incorrect position, we'll actually output a secondary output It's kind of a continuous offset vector that lets us, I would say, snap onto the object of interest. All right. So what we're going to do is, if this was our sliding window, we will also, not only will we predict that there's a person in that window, but we will also predict this, this bright blue vector that tells us how to slightly, move our window to really just snap perfectly onto that person. I'm going to call these sliding window positions anchors, because that's the sort of how they're called in the ConvNet world. I'll talk more about that. Okay, so that's sliding windows. It's kind of been around for ages and ages, I would say. Going back to, actually I don't even know when it goes back to, but I was reading papers in the early 2000s where kind of computer vision people were using this all over the place. So it's been around for decades, and what are we doing new with ConvNets? And I would argue that today the kind of predominant way to do things is not that different, actually. So we're still using sliding window positions. The difference is we're using ConvNets to do the sliding, capture the sliding window behavior. So the way these things work is we're going to take an image, we're going to plug it through some ConvNet. Usually this is something, like a famous ConvNet, like VGG or Inception or ResNet or whatever you might have. And the effect of this is to extract a tensor of features that sort of capture the features of a sliding window across your image, right? And we sort of want to capture these large contextual regions to feed into our feature extractor. And what's cool is that this is sort of automatically captured by convolutional neural networks. And the deeper the networks that we use, the larger the receptive fields that we have to, from which we can extract features. All right, and then usually something simple happens. So if we extract this tensor features, we might take this little blue column of features for one bounding box location up here, and we plug it through a fully connected layer to predict our classification. So classification is into a K-classes, where one of those K-classes is usually a background class. It's like a kind of a catch-all, I don't know class. And then there's the box regression. So there's a continuous offset prediction, which lets us snap that anchor kind of to really fit onto the object of interest. Okay. Okay, so I'm going to talk on this in more detail in the next few slides. Here's kind of the cartoon view of what I just showed you. So here we have our image, and the red kind of squares are our anchors, or our sliding windows going across. And what we want to, and what happens is when we run our ConvNet on this image, it's extracting features, which is this blue column, from this slightly larger window that we call receptive fields, and then to this blue column, which is just a feature vector associated with this receptive field, we're applying we're multiplying it by a weight matrix W class, for class prediction, and then we're applying a softmax layer, and this gives us some multi-way classification for what's there. It might say, oh, it's a person, or it's a background, or it's a car, right? And then to predict the continuous offset, same thing. We don't do the softmax, right? So we just multiply it by weight matrix W lock in this case to Vij. Very simple. Questions so far?
I have a question. Like you mentioning position and anchor, would you also get like the scale? Like do you want the box to be bigger?
Yeah, good question. So let me talk about, I'll get to all of that. So right now we're sort of thinking of it as just happening on one scale. Let me get to that in 2 or 3 slides maybe. Okay, so so early on, and when I say early on, I mean like 2014, people typically, if you look at some of the early, say, multi-box papers, people would actually use a different W class and a different W lock for every Vij. So every position, kind of every sliding window position would kind of be associated with its own anchor, with its own weight matrix. And what's kind of cool was at some point, people, actually a lot of papers realized, oh, we should share these weight matrices across all locations, right? And not surprisingly, if you do this, you can write it as a convolution. And so specifically, what I'm saying here is, if our anchors, if our red boxes here are all of the same shape, they're sort of arranged regularly on this grid, and they all happen to be contained and centered inside the receptive field, then it makes a lot of sense to use a shared W-lock, W-class for every anchor, in which case we can sort of just have this simple expression where we're applying to this input, this tensor of features V, we're going to apply just one conv followed by a softmax layer. And then for the continuous offset, we're just applying just the conv with different parameters, and that's it. And so, so this is very simple. It's sort of, if you're doing this in Keras, it literally is a few lines. Okay. Okay. So, to your question of how do we handle different scales and aspect ratios, there's a few ways to do this. So one is kind of natural one is let's use different W-lock and W-class to handle each scale / aspect ratio. And so specifically, what we're going to think of is having a grid of sliding windows again. And here we're kind of drawing a grid of sliding window centers on these blue points. And then around each center point, I'm going to arrange boxes or anchors of different sizes, different aspect ratios. All right? And so now what we're going to be thinking of is we're going to take this, tall and skinny window. We're going to slide that across the image at each grid position. We're going to get our predictions. Then we're going to do the same for this, also tall, slightly less skinny window. We're going to slide it across. Each time, we're going to use a different set of conv parameters. I'm realizing I have a typo here. There should be a conv here. Each time, we're going to use a separate set of parameters and do, and just output a lot more kind of predictions, one for each discrete scale that we care about. All right. And on the offset, we're not predicting just 2D offsets. We'll predict 4D offsets. So X, Y with height kind of offsets. Yeah. Okay. The other thing to do is another trick that often happens is we'll attach these predictions to different layers in the convnet. So one paper that came out in 2016, called the SSD paper, the single shots detector paper, I think, ran an image. This is an image running through VGG16. And what it would do is for this 38 by 38, I guess I'm not drawing the 38 by 38. For this 19 by 19 feature map, it put a 19 by 19 anchor grid, shown here. Around each point in this 19 by 19 anchor grid, it had a few aspect ratios, a few sizes. It ran prediction there. And then for the rest of VGG, it would do the same. So, and then there was like a 10 by 10 layer. So it would draw a 10 by 10 anchor grid. And this time, for the 10 by 10 one, you would draw slightly larger anchors. And so the hope of the SSD paper was that by having all of these kind of anchors of different scales, different aspect ratios, different positions, it would be able to kind of have very good coverage of kind of all the shapes that bounding box could be, and do a good job that way. All right. Okay, I'll come back to SSD in a bit. So the other kind of missing part of the equation is how to train this thing. One of the important things, and this is really just in the guts, so most people, I think, don't, you might not learn about this too carefully in a class, but I like to go into it just to really give a sense of how this works. So the picture here is we have our anchors here in red, and at training time, we're given access to some ground truth boxes, right? So on an image, we might know a human's labeled, oh, there's a human here, and there's a car here. Or, okay, human here and human here. I guess that's what I'm trying to say here. And what we want to do is we want to match the anchors to these ground truth boxes. And so usually we match based on something like overlap area. I'll talk more about that, or Euclidean distance. So just finding like the kind of in a greedy way, what's the ground truth box that matches each anchor? and then remembering that somewhere, right? And the other thing is we want to come up with these location targets or these continuous offsets. So for example, if I know that this blue box matched to this red box, then I want to remember their offset. So take the ground truth x min minus the anchor x min, ground truth y min minus the anchor x min or y min, and so on. Okay, so all this stuff I'm going to store, and then when I run prediction up my convnet, I can just I can sort of have as classification targets this matrix and regression targets this other location targets matrix. Okay, all right. Here's kind of an example loss. There's like so many loss functions that people use in this literature, but kind of one very standard one might look like this. So we have this is called our location loss. So we're predicting a t lock. Sorry, no, we're predicting a w lock times vij. So this is our feature vector multiplied by our weight matrix for the location. And our ground truth offset is t, our target lock, right? And we might minimize L2 distance. And we only do this for anchors that match something. So this delta sort of is on if an anchor A has a matching ground truth box, and it's 0 otherwise. The other loss that we have is just standard, something like softmax cross entropy. So here we're again predicting logits using our W class times feature vector Vij and comparing that against our classification targets T class. Usually you might have some weights, alpha and beta, to trade off the impact of each of these loss functions, and we average this loss function over all of the anchors, over all of the images, and then run something simple like SGD, could be Atom, could be any number of optimization algorithms. Okay, so a little bit more in detail about these loss functions. So typically we're not actually minimizing loss in kind of Euclidean space. What we do instead is we predict some kind of modified versions of the offset. Okay, so here's a standard thing. We use we encode the ground truth center of the target box in normalized coordinates. So we're dividing by the width and the height. I'll go through this pretty quickly. We also want to encode the size of the ground truth box in log coordinates. This has the nice property, which is that if we were minimizing Euclidean coordinates for detection, then what happens is for a small object, if you're off by, for a large object, if you're off by 3 pixels, it's not so bad. But if you're predicting for a small object and you're off by 3 pixels, then Euclidean distance doesn't care, but this representation will care a lot because it's done in log space and it's done relative to the width and height of the box in question. All right, so this is why these types of weird-looking loss functions are very popular in bounding box detection. Typically people use a Huber loss, and so this is to penalize things slightly less if they are kind of completely off, right? So Huber, it looks like a quadratic from 1 to -1, and then past that it's just L1 penalty. All right. Back to the classification loss. The main challenge here is dealing with class imbalance. So one kind of problem that all object detection models have to contend with is that anchors are almost always negative, right? So kind of a typical number of anchors that you might have is 50,000. And you might have 10 objects in your image. And so then the ratio of positives to negatives is 50,000 to 10. It's really ridiculous. And then the model looks at it and it says, okay, I can get almost perfect score by predicting everything to be negative, everything to be background. So I'm just going to do that. And that's not good. So somehow during training, you sort of have to tell the model, okay, I care more about the positive predictions than I care about the negatives, right? A few ways to deal with this. I'm just going to kind of quickly go over some of the main ones. So one is to subsample the negatives. So if I have a bunch of anchors that are considered to be background according to the ground truth labels. And I just randomly pick a few. And so I'm going to pick a number that's comparable to the number of positive anchors in that image. That's option number one. Option number two is to downweight the negatives. So I can apply kind of a smaller scale to every negative anchor in my image. Option number three is online hard mining. So in hard mining, what I'm doing is I'm looking at the negatives and I'm going to hunt for the ones that are most incorrect. So if I'm making a prediction that is and I think it's a positive, but it actually should be a negative, then that's considered to be a hard negative. And I'm only going to consider those negatives. All right. And then finally, which is the most popular one these days, is called the focal loss function. And focal loss looks like this. And the way to think about it is that it's a little bit like online hard mining, and it's a little bit like downweighting negatives. So what I'm going to do is I'm going to give less weight to easily classified anchors. All right. So this blue line is kind of the standard cross entropy loss, whereas this green line has been shifted so that if we're already doing well on some anchor, usually that anchor is a background anchor, then we are going to assign it much less of a penalty at training time. Okay, another kind of practical issue that we have to think about is this weird thing, which is that after you've done your training and you run your inference on a new image, you're going to get a weird effect, which is that you'll have a lot of identical predictions around the same thing. All right. So around this person, it would be typical to get maybe 5 or 6 boxes all clustered around, but not exactly equal. And that's natural, right? Because we might have kind of multiple anchors that think they should be regressing using this offset mechanism to the same person. So they all sort of regress, but they're all a little bit off, and they get something kind of like that. So the way we handle this is a big hack. What we do is we remove detections if they overlap too much with some other detection that got a higher score. All right, and so this algorithm today is known by non-max suppression. I call it a big hack. Everyone does it. I think it would be really cool if someone showed how to do this in a principled way. I haven't seen it yet, though. So the way non-max suppression works in detail is what I'm going to do is I'm going to run detection. I'm going to get a bunch of anchors, a bunch of detections as the output, and they'll have scores coming from the sigmoid or the softmax nonlinearity at the end. And I'll sort them. So now I'll have a person with score 0.9 and another box that detects the same person with score 0.7. And then I'm going to iterate through the sorted detections, and I'll just throw out a detection if it overlaps with an already selected detection by some amount. And again, I'll talk more about how to measure overlap in a bit. Good. So this is kind of a cool research problem if anyone wants to think about it. I think what we know about it is that if you're using non-max suppression, there is automatically a limit on how accurate you can be, right? Because if everyone is just like next to each other, if they're hugging each other or something, you can automatically not detect that because non-max suppression will just reject these detections. The other weird thing about non-max suppression is that we apply it independently to classes by default. So what that means is if you have two classes that look very similar, let's say wolf and dog, right? So you can expect that your detector will often confuse your wolves and your dogs together. And then in this picture, what will happen is you'll have a bunch of wolf and dog boxes all kind of clustered on the same thing. And they will not be able to suppress each other. So you'll always get, even if you run non-max suppression, you'll always get both a wolf and a dog detection at that spot. Okay, back to this picture. So this picture, again, is this, I think, high-level view of SSD. This is one of the most popular ways, which is just what I told you. So take your image, run it through your feature extractor, apply a conv layer, get classifications, apply another conv layer, get box offset and run Max Suppression, and you're done. It's very nice. If you've seen papers called multi-box or YOLO, V1, V2, V3, RetinaNet, all of them do something like this. They might use different settings for the anchors. They might use different settings for the feature extractor. One paper uses VGG, one other paper uses Inception, but they're all doing this picture. All right. Okay. The other popular one is faster RCNN. I saw at least one poster today that was using faster RCNN. And it's sort of a similar picture with an extra twist. So this part, the blue and the pink boxes are the same. What we're doing is we're running SSD, but at this point, instead of running a multi-way classification, instead of trying to predict car, person, dog, horse, whatever, we're just predicting whether there's an object here or not. And once we've predicted that there's an object there, we will essentially crop out features from the result of the feature extractor and pass it through more layers. All right, and then at the end of this more layers, we're going to do our multi-way classification and our multi-way, and our offset prediction. And the benefit of doing this is, there's a few benefits. One, for example, is you're kind of doing more hard work for regions of the image that you think might be positive, right? So this is really popular, and it's actually, I would call this basically, it's been the state of the art for many years, since 2015. Only recently have people started kind of doing something significantly different from this if they want very good results. Here's another one, RFCN. I won't talk about this one too much. It was popular at some point. It's sort of fallen out of popularity. The difference compared to faster RCNN was that instead of copying, so faster RCNN, you crop some features and put it through a convnet. And here what you're doing is you're putting the features through more conv layers and then cropping at the end in a certain special way that I won't go into, and then doing the prediction. Anyway, so I'm not going to dwell on RFCN. Let's talk about how to understand if our detector is good. So first you need a data set. There's been a lot of data sets over the years. When I was in grad school, the popular one was Pascal VOC, 5,000 images. At the time, I trained a detector, and it took a month, and it took all of our graphics labs machines to do it. And it was ridiculously bad at everything, I should say. Today, what's more popular is the COCO dataset. It has a lot more images, 120,000 images. And that's been kind of the main thing that everyone compares their detectors on. But new ones are coming out every day. So Open Images came out from Google. They're still releasing versions of this. This one has 600 classes, 1.7 million images. It's really, really, really big. So if you're interested in a data set, I would recommend checking that one out at the very least. I'm going to skip this slide. OK, so how do we know if our model is good? For classification, this is an easy problem. OK, so we have 4 images, and we're going to run our classifier. Our classifier is going to say cat, dog, cat, which is wrong, dog, right? Or sorry, cat, which is right. And then accuracy is just we just compute the accuracy. It's very easy, 75%. How about detection? So detection is a little bit harder, and I know some of you probably have seen this stuff before. I just want to go through this in detail just so everyone can sort of see this. So for detection, metrics need to be handling location errors. Okay, so if my ground truth dog is this green box and my detected dog is this pink box, well, it's sort of right. It's kind of getting there, but it's not quite there. So should we consider that detection to be correct or not? The other thing that we need to account for is this phenomenon of overprediction and underprediction. So in this setting, we have 2 ground truth dogs, and my detector, which I know people can't see that well, is this pink line here. And the detector just returns one dog, right? So here we're underpredicting. We're not getting one of the important dogs. Alternatively, what can happen is we're overpredicting. We're imagining a dog somewhere where there's not a dog, right? So the way we measure this typically is using the IOU measure, the intersection over union score, okay? And what we do is we just take the intersection of the predicted with the ground truth box. So that's this blue region here. And then we take the area of the union of the two boxes, which is this orange thing here, all right? So I'm plotting it nicely here. Blue divided by orange area. That's the IOU. We know that if the IOU is equal to 0, then your boxes are, then your prediction was completely disjoint from the ground truth, so you're way off. And if your IOU is 1, then it means you're perfect. You got it exactly right, right? Typically, we have a threshold, alpha. So we say that if your detection got IOU with the ground truth greater than some alpha, like 0.5, then you're considered correct. And people use different alphas depending on their application. So here, just to give you an idea, IOU 0.9, basically it's almost perfect. You basically can't see the difference between the prediction and the ground truth. If we relax that a little bit, IOU 0.7, you can tell you're doing really, really well. And then by IOU 0.5, this means that you're allowed to be a little bit sloppy. You still have to get it kind of more or less, but you're allowed a little bit of slop, right? Okay, just some more examples. So again, IOU 0.5, 0.7. This is 0.95. Again, almost perfect prediction. All right, so what do? Well, we take our IOU kind of definition of correctness or not correctness, and we use it and label all of the examples in an image. And we use it to kind of declare instances as true positives or false positives, right? So for example, here, here's a green box. It's a dog, right? It's a ground truth dog. And I detected that dog pretty well, so that's a true positive. However, I detected 2 dogs where there was just one. So one of those is a true positive, one of those is a false positive, all right? And the way I'll decide that is which one had higher IOU with the ground truth dog. This one, I got perfectly true positive, perfect, right? And this one, there's 2 dogs, but I detected one. I put 1 box around both of them, and that's really bad because not only did I get a false positive because it didn't overlap with either of them with 50%, but I also missed 2 objects that I should have gotten, right? Okay, so that's how we declare whether things are false positives or true positives. And then we just care about 2 things, precision and recall. So precision is the number of true positives divided by the number of, basically, of the detections that we produced, how many of them were correct, right? So if I produced just 1 detection, maybe I missed everything, but that 1 detection was correct, then I have 100% precision. I'm very happy. On the other hand, recall is of the ground truth instances in my data set, how many of those things did I actually manage to detect, right? And that's number of true positives divided by the number of ground truth objects. These are 2 quantities always between 0 and 1. And there's kind of a trade-off between the 2, right? So if you imagine sorting your detections from high confidence, 99% dog, all the way down to 2% tortilla, then usually the way you declare, you sort of say whether something's a detection is use threshold on score. So if I put my score threshold here, I have 2 detections. I detected a cat and a dog. Both of them are correct, so I have perfect precision, but I missed this cup, okay? So not so good. However, if I increase my score threshold, I'm going to start kind of letting false positives leak in. So there's kind of this fundamental trade-off between between precision and recall. And hold on. Yes. So I can plot this. So I can kind of sweep my score threshold all the way from 1 to 0. And by doing that, I'll trace out this precision recall curve. So I'm going to get a bunch of pairs of kind of precision common recall. I'll plot that thing on this precision recall curve. And the thing that most people in the object detection community care about is this thing called AP, which is average precision or area under this precision recall curve. We know that AP is always, between 0 and 1. We know that higher AP is better, so we like higher AP. And the other thing, just to remind you, is this is always relative to some IOU criterion, some alpha. So we usually say AP at 0.5, and that means that we computed average precision relative to this IOU threshold of 0.5 that we use to declare whether something's a true positive or not. If we have multiple classes, then we do this independently for every class, and we average them to get something called mean AP. And so here, these are just kind of typical, training runs I might have. And here we're evaluating AP for airplane, AP for apple, AP for backpack, AP for bananas. Blue is orange is the training mean AP, and the blue is the test AP, right? And then what we're going to do is we're going to average those numbers. And I can do that for different IOU thresholds. So here I'm doing the average or the mean AP at 50% IOU. Here I'm doing the mean AP at 75% IOU. And you'll notice that 75 is a harsher threshold than 50%, right? So these numbers are smaller. So here I'm getting to about 35% or maybe 40% mean AP, whereas with the 50% threshold, I'm getting to something closer to 55, I would say. Right? And then the final thing that people do is they'll actually average all of this over many IOU thresholds, right? And so here I'm averaging the mean AP at 50%, at 55%, 60%, 65%, and so on. And most papers these days in the vision community, when they report mean AP, they're actually using this super complicated number. So if I tell you, something is, my detector got a 35%, that doesn't mean it's bad. It doesn't mean that the accuracy was 35%. The 35% is a super complicated thing where you're averaging over crazy, 95% threshold where you're almost never going to be perfect. It's sort of an art it takes some art, some experience to interpret these numbers. Yeah. Okay, so just to give you a sense, here are different architectures running on the same image. So here's that kite image again, and so for here we're running kind of one of our not so accurate algorithms, SSD with a mobile net feature extractor at low resolution, so 300 by 300 input, and it gets to a mean AP of 21 on this happens to be the COCO data set. On the other end, we're running a faster RCNN model with an Inception ResNet v2, which is very heavy backbone network, and we're getting to a mean AP of 37. And you can just sit and stare at these results a little bit. One thing to notice is that SSD models are actually not bad. They're doing a reasonable job of getting these people. You might be able to see some differences, but by and large, across the board, I think they're not doing that badly. If you're picky, you might spot some kind of, for example, this model thinks this thing is a person, where in fact it's a kite, right? The difference kind of sort of appears when your objects get small. So here in this image, again, doing a pretty reasonable job if I were to just show you this image. But then if I show you this faster RCNN Inception image, I start seeing, oh, there's a cup on the table, and there's a bottle, and there's a wine glass, right? So there's all these little things that this heavier model is seeing that my lighter weight SSD model isn't seeing. And I'll talk a little bit more in the next slides, but kind of this is a big thing. So people might choose to run the SSD model if they feel like they're the things that are important to them are going to be large on the frame, right? Or if they're going to be close to the object. Okay. So here's my practical tips and tricks section. How to select a model, and this is related to the two images that I just showed. So first, when you choose a model, you need to choose a meta architecture. So this is usually SSD, faster RCNN, or RFCN, something like that. Then you need to choose a feature extractor. So it's going to be like VGG or ResNet, Inception ResNet, something like that. And then you need to choose an image size. So if you have a lot of big beefy GPU, you might choose to use 800 by 1296. If you have a cell phone, you might choose to use something smaller, right? So you sort of have to think about all these things. You have to think about memory constraints, what device you have. So sometimes I run on my laptop. Sometimes I'm training in Google data centers, and I'm using a TPU. I'll talk more about that tomorrow. On the other hand, I might be just kind of taking that model and deploying it on a Raspberry Pi, and that has its own constraints. So these are all things that we sort of have to think about. And to help things out, a few years kind of back, we made this picture that summarized the speed and accuracy trade-off of all the models that were available at the time, and this picture has changed, not only because there are more models, but GPUs have gotten faster and the kernels have gotten faster. But the overall kind of lesson is still holds for a lot of these models. So first of all, there's kind of this curve of this kind of Pareto optimal curve, right? So you sort of always want to be choosing models on that curve, because if you're on that curve, you cannot get faster without sacrificing some accuracy, right? So somehow you want to be there. Some models that we found at the time were really good were SSD MobileNet. So it was not so accurate, but it was very fast. On the other end was faster RCNN with Inception ResNet, which I also showed you, which was super, super accurate. But whenever we ran it, it was about a second on an image, back then anyway. We actually took a combination of faster RCNN Inception ResNet models and ensembled them to win the COCO 2016 Object Detection Challenge. And back then, by ensembling so many things together, I think it was like 20 minutes per image, which is pretty insane. But we got slightly higher than this curve. Okay, I guess I just talked about that. All right, another trick is to initialize from kind of initialize your weights in a nice way. So typically you initialize from a ImageNet pre-trained feature extractor. So if you have VGG as your feature extractor, you'll pre-train VGG on ImageNet, take those weights and start from there. There's been a number of works that try to kick things up a notch by pre-training on a larger data set. So here we have an example training on ImageNet plus an internal Google data set with 300 million images called JFT. I don't know if it's worth it, but it helps. So it was a lot of work to train on that large of a data set, but it does kind of improve our final performance by a few percent. So if you have the resources to do that, then it doesn't hurt. And you just have to do it once. If you want faster speed, lower resolution is usually the first thing we go to. So often we'll run at 640 by 640, for example. But if we want to run things on a cell phone, we'll just say, oh, let's use it on 320 by 320. And the trade-off is we'll miss the smaller objects on average. I'm going to, no, I'll go over this. So in faster RCNN, remember we predict a bunch of class agnostic proposals, and there in the first stage of faster RCNN, we don't care about what class it is. We don't care if it's a dog, we don't care if it's a cat, and then we take a bunch of those crops and run them through the second stage. And when the faster RCNN paper first came out, they recommended using 300 crops, finding 300 objects and then kind of running them all through the second stage. And this, and doing that still gets really good results. But what we found later on was that if you use fewer proposals, like if you reduce that to 50 or 100, you can get almost as good performance. Here's the number of proposals, and here's the overall mean AP. You can get almost as good performance at a much, much faster runtime. Another trick is to use true convolutions. And so here, and this is related to the dilated convolutions that Aaron mentioned earlier on. So it's useful if you can have more sliding windows in your image. Now, typical convnets have these stride2 operations. So every now and then you might have a conv with stride2 or pool operation that decreases the resolution of your feature grid by a factor of 2. But if you're doing object detection, you want high resolution. So somehow you want to not have these stride2 operations. So you can say, OK, I'm going to take my stride2 and just convert that to a stride1 convolution. But that's not so good because it reduces the effective receptive field of your prediction. So in your original image, here you're using kind of most of your image. But if you're making the first layer a stride2 operation, sorry, a stride1 operation, then suddenly you're using half the pixels to do your prediction. You're looking at a much smaller piece of your input image, and that hurts your accuracy. So what people do is they use this trick called a true convolution, which comes from French. It means convolution with holes. And the trick is at the second layer here, what we're going to do is we're going to insert a hole, these black X's here, and we're just going to skip over those when doing our convolution, essentially. And that lets us keep the size of the receptive field the same. OK, how am I doing on time? Am I 4? Half an hour, OK. All right, so I'm going to talk about, I'm going to plug my team at Google a little bit and then move on to other topics. So I've been working on democratizing object detection. When I came to Google, there are a lot of teams that are starting to do it, but it was really specialist knowledge, and every team had to hire their own PhD in object detection to train their object detector. So we came in and we want to build a kind of a unified code base. And what's really cool is now today that thing is open source, so you can do it. You can use it too. You just have to go to, well, don't write this down. You just have to write TensorFlow Object Detection API, and you can find our code base online. I'll just give like a few words about what this looks like if you're a user. Okay, so we have these configuration files, and you can easily modify the number of classes that you predict for. So here, maybe you have a self-driving application. You might want to predict cars, people, stop signs. You can say what resolution of image you want to use to kind of adjust for the mobile use case or not. You might decide to use faster RSNN, but you might decide to use something else. It lets you train on your own data set, so you can kind of adjust learning rate to your own data set, or you can initialize from your own pre-trained model. Super, super easy. Kind of if you know TensorFlow, what our thing is doing is it takes one of these protos and converts it into a TensorFlow graph. And then you can use that graph in certain binaries. So you can train with that graph, or you can evaluate that TensorFlow graph. You can export it to serve on device of your choice. And the other cool thing that we provide is a detection model zoo. So if you just don't want to train anything and you just want to use a model out of the box and run it on your data, well, you can do that. We have a bunch of models. Most of them are on Cocoa, but a few other ones too. For example, we have something that's trained on the OpenImages 600 classes. We have this model that's trained to predict 3,000 species. I'll talk more about this particular project a little bit tomorrow. What's been really rewarding to me is seeing what other people have done. So people have put up tutorials on this. So you can go on YouTube and kind of get tutorials on how to use the TensorFlow Object Detection API. They've done a much better job of explaining it than I do, I must say. Some people have used it to detect traffic in New York and detect kind of specifically illegally parked traffic in New York so that they can be ticketed. And I'll just show this video. I think I have to go here and click it physically. This is my favorite one. Okay, I'm going to stop it there. Okay, change of pace. We're going to talk about segmentation now. It's a segue into segmentation. And segmentation is somehow a more detailed operation compared to object detection, right? We want to label every pixel with the class that it belongs to. You can imagine that it's more useful than bounding box detection for image editing operations, for example. So this is an illustration of the bokeh effect that a lot of professional photographers use. The way that works is if you set your aperture to be large on your camera, then you can effectively bring one kind of depth plane into focus and defocus. You can blur everything else out. Why would you want to do that? Well, you want to somehow call attention to, or you want to emphasize a certain subject in your photo artistically, right? And so, for example, here we have a subject who's this woman, and we might want to keep her sharp and blur out this graffiti in the background, right? And what's cool is today you can do that if you use an Android phone. The way that works is not through physics. What we're doing is we're just actually running segmentation on the image that you get from the phone. It figures out where is the human in this image. It keeps that human sharp and it blurs out everything else. So here's the effect. It's not a super strong effect right now, but what you can see if you look up close is this, her eyes are in focus, but the coffee has been blurred out, for example. In this case, it does not. I'm sort of waiving some details because, half of this pipeline is person segmentation. The other half is depth prediction, which I'm not going to cover. So they're also doing monocular depth, and that's actually a combination of neural nets, but also there's kind of two lenses. So there's like a physical part of that to predict depth. And then they're stitching all of that together to get a good depth performance here, or blur kernel here. Okay, another thing you could do is you can be fun and substitute the background for something else. And I believe this is available on YouTube now if you want to make your own videos on YouTube. Okay, so how do segmentation models work? And interestingly, they're even though they're detailed, conceptually they're a lot simpler than object detection models. So kind of a typical pipeline is as simple as this, where we take an image, we plug it through a convnet. At the end, for every pixel, we're going to predict. In this case, it's going to be a binary output, so background or person, right? And then that prediction goes into sigmoid cross-entropy loss function. Super simple conceptually. The tricky part is how to get this to work really well. And to get it to work really well, there's a few things that you have to take care of. So one is high-resolution outputs. And this is even more important with segmentation than object detection. So pretty typical for a convnet to kind of reduce the resolution by a factor of, say, 32. So if my input image is 640 by 640, my output feature tensor is going to be something like, 20 by 20, right? And that's way too small to have a detailed segmentation map. And so what we really want to do is to kind of keep it pretty large. So, maybe predict at 320 by 320 or something like that. And to do that, we can use things like true convolutions in order to also have a large receptive field. The intuition about the large receptive field is if I want to, for example, predict that the white pixel on this person's eye is part of a person's eye, then somehow I need to be able to zoom out and look at his face to realize that it's a face to make a prediction for that particular pixel. Right, and the other thing that we need to do, and this is going to be very hand-wavy, is to access low kind of edge-level features and also access high-level semantic features. With segmentation, we care about the edges and kind of their geometry, kind of more in a detailed way. Okay, so here's just one cartoon from one of my colleagues' papers, Jay Chen. This is called DeepLab v3. And it's not the only way to do semantic segmentation, but it sort of captures these three desiderata. What he's doing here, I'm saying he, but there's actually a huge team that works on this. So what he's doing here is he's taking an image, he's running it through kind of a more or less a typical convnet. And then what he's doing here is he's running true convolutions to get progressively larger and larger receptive fields and combining them. And then he's running these up convolution operations, which I won't go into detail about, that increase the resolution. But on the way to increasing the resolution, he's combining it with these low-level convolutional features for final prediction. And so the size of his prediction is comparable. It's actually not the same, but it's comparable to the original input image. And so just a few words on how to evaluate this thing. Again, it's actually easier with semantic segmentation. So here, we're going to use the same thing, IOU, but we're going to use mask IOU. So if I have my predicted pair, and I'm comparing that with my ground truth pair, then I want the intersection of the pairs, which also looks like a pair, surprisingly, and the union of the pairs. And I'm just going to take the ratio, and that's IOU. Same properties, so my masks are disjoint if the IOU is 0, and my masks are kind of perfectly aligned. They're identical if the IOU is 1. All right, and so typically what we do is we take the so-called mean IOU, which is just the IOU averaged across the different classes. In this example, I have sky, building, pole, road. So I'm going to take I'm going to take my predicted road and compare that against my ground truth road, compute an IOU, right? And then do the same for cars and sidewalk and vegetation, and average all those numbers. Very simple. If we look at DeepLab again, here's some of the results that you might see, and I'm not showing you the history here, but it's doing pretty well. So, for example, some of these gaps between these dogs managed to be segmented out fairly well by this particular model. On Pascal, these days, we're getting to about 90% mean IOU. So doing very, very well on this particular task, on that data set. Still not perfect. So, for example, if you come over here, there's a gap between this person's arm. It doesn't show up here. So there's still some work if people want to work on that. And the other, so there's actually two versions of segmentation. So that was semantic segmentation. But actually, you can imagine that if you're doing image editing, you might want to operate on one person at a time rather than if you have a crowd of people as in this image, right? We might want to adjust the settings for each person individually. And that problem is called instance segmentation. So here's kind of the diagram of all the problems. We have original classification or image tagging, which might have told us person, sheep, dog. Then we had bounding box detection. Then we had semantic segmentation, where all the sheep are labeled blue, right? They're all kind of grouped together. And then finally, in instance segmentation, what we're doing is we're predicting an additional instance ID per instance, and that lets us separate, sheep number 1 from sheep number 2. Okay. So the way to think about the difference between semantic and instance segmentation is that we typically think of semantic segmentation as being good for stuff categories. So stuff categories are things like here's platform or sand or cloud or sky, things that don't naturally separate into atomic instances, right? And so typically that stuff is considered stuff, right? And then things are like people or chain or I don't know, basketball, if that's a basketball. So that would be handled by instance segmentation. And for instance segmentation, one of the leading models today is just a simple modification of faster RCNN called mask RCNN. So whereas faster RCNN, we would crop the features out for a particular object and run them through a secondary convnet to predict class and bounding box. With mask RCNN, we'll take the same features and apply a few extra layers to predict a mass prediction. Okay, so our output in this case for the COCO dataset might be something like 14 by 14 by 80. 80 is the number of classes in COCO. 14 by 14 is our mass prediction, and this turns out to be relatively state of the art. So, for example, here's faster RCNN running on, I believe this is the A20K dataset, which I haven't talked about, but it's a lot of kind of inside category type datasets. So so there's a refrigerator, a television, cabinet, and so on. All right. Now I'm going to sort of end this section with the discussion of panoptic segmentation. And panoptic segmentation is kind of a new thing. So it's not as popular these days, but it's sort of gaining steam. So I think in the spirit of introducing things that are going to be big in the future, this is one of them. Panoptic segmentation is the problem that brings stuff and things together, right? Specifically what we're doing is we want to assign a category ID and an instance ID to every pixel for categories that happen to be considered stuff, and it's up to us to decide what are stuff categories. We're going to ignore the instance label. How do you measure panoptic quality is an interesting research question. There's a paper called Panoptic Segmentation that sort of tries to answer this question. I'm not sure it's the final word on this question, but for thing categories, what we know is that instance segmentation is applicable, and therefore map based on mask IOU seems to be the right thing to do for things. The problem is map doesn't really make sense for stuff categories because stuff categories don't come with a nice score for every segment, and therefore we can't sort things and apply map and mean AP in the same way. On the other hand, for stuff categories, mean IOU seems to make a lot of sense. But the problem with mean IOU is we don't really account for false positives or false negatives, I think, anything like that. And so that's not quite the right thing either. And what these people propose from Facebook is this measure called panoptic quality, which combines sort of the best of both worlds. What we're going to do is we're going to go over the ground truth masks and the ground truth and the prediction masks, and we'll match them. We'll match two objects if their IOU is greater than some threshold, in this case 50%. And this 50% is chosen such that we're never going to match them more than one object, right? And so here, we see the blue object matches the blue prediction, orange object matches the orange prediction. There's a false, we're imagining some kind of yellow thing here which doesn't exist in the ground truth. And there's also some gray area here that we just did not see in the prediction, right? And so this so-called panoptic segmentation quality is going to go over the true positives. It's going to it's going to average their IOUs, and it's going to normalize it in a certain way. It's going to divide by the sum of, by these counts, essentially, all right? And so therefore, it's taking account IOU, so segmentation quality, but it's also accounting for false positives, false negatives in a smart way. It turns out, so you can write it more generally this way, and it turns out that if you think things through, this is writable also as the product of the F1 score times the mean IOU. F1 score is not so popular in the computer vision literature anymore, but kind of it used to be a kind of a detection metric that a lot of people used. So it's really just kind of combining a detection metric with a segmentation metric by multiplying them. All right, so I'm going to move to key point prediction as kind of the last part of my talk. This is just my, oh, it's not showing up. Never mind. Okay, so this is key point prediction. We're putting we're drawing a skeleton on everyone in the image. So it's just people specific. One way is mask RCNN again. So people like to take mask RCNN and apply it to their problem of choice these days. And here, what we're doing is we're taking the features for each bounding box. We're running it through yet another several layers of convolution. And what we're going to do is we're going to, for every possible key point in a person, and we have to decide up front, oh, we're going to predict for neck, and we're going to predict for left shoulder. We're going to predict for right shoulder, right? So what we're going to do is predict a heat map for each of these key points. So right wrist heat map, a left wrist heat map, a left eye heat map for every instance, okay? And it's as simple as that, super, super easy. And it works pretty well. But what I really want to talk about is this other way. So mask RCNN is called a top-down approach. And it's top-down in the sense that we're first detecting people, then for each person, we're trying to understand where is the key point, where are the key points in that person. For bottom-up approaches, it's kind of the opposite. So here, what we're going to do is we're going to predict all of the right ankles in this image, right, in blue here. And we're also going to predict in a separate map all of the right knees in this image in yellow, or in green, I guess. And then in the second stage, we're somehow going to post-process these predictions to put them together, to group them, right? And so, for example, here, what we'd really like to do is to make sure that Leo Messi's right knee is associated with Leo Messi's right ankle. And if we kind of get it wrong, then we're going to get a bad skeleton, right? Oops. Okay, so here's just one example, again, by my colleagues. This is George Papandreou and Tyler Zhu. So what they're doing up here is they're predicting heat maps, again, for every key point. And then additionally to that, they're predicting a so-called mid-range offset. And so what that looks like is for every left elbow, they're going to predict a vector such that if I take the position of my left elbow and add it to that offset vector, I'm going to predict my left shoulder, okay? And they're going to predict relations along every, you can think of every bone in the skeleton. So I'm also going to take my right foot and predict a vector that tells me if I know where my right foot is and that offset vector, I will know where my right knee is. Did you have a question? Question? Okay. And so anyway, we're going to take these heat maps, and using the heat maps plus these offsets, I won't go into the decoding process, but you can sort of imagine that I can take one thing that I detected well. So if I detected a nose, then I sort of just follow the skeleton down. I use the offset from my nose to the neck to predict where my neck is, and then recursively fill out my skeleton. It's a little bit like that. I won't go into the details. But it works pretty well. It works surprisingly well. So here, this is again the COCO data set, but on key points in the COCO data set, we are getting to around 68% AP in the best of cases compared to a masked RCNN baseline. All right. Here's another related bottom-up way that came out recently. So this is by a team at University of Texas, Austin, and they did a similar thing. So they're predicting heat maps for every key point in the human body, but they add a key point, which is the object center. So they're taking the center of the person, and they're predicting, in addition to that, the offset from the center to each posed key point. So that makes it a little bit easier. You don't need to reason about this crazy skeleton and offsets along the skeleton. You just have to remember, you just have to predict the center and then kind of predict from the center using the offsets to get all the posed key points. And then they added another thing, which is that since they have bounding boxes in the COCO data set, they also predict from the center. They predict the object height, and they predict the object width. And I won't, okay, so here's how they do. And if you look at the bottom rows, you can sort of see it's really, really good performance. Even if you kind of look carefully, it's quite spectacular. People are really close to each other. There's a lot of people. It's doing quite well, even on the small people in the background. But the funny thing is this top row, they just apply the same model to things with no key points. So now the center is just the key point, and they're doing bounding box detection. And they're applying it to things like, all the COCO objects like oven, dining table, orange, whatever. And the surprising thing is that this performance is really, really good. So here, this was the YOLO. I didn't talk about YOLO too much, but YOLO is kind of an SSD style model. YOLO, here's RetinaNet, which is also SSD style, and here's faster RCNN. And CenterNet, which is this, this new method that was originally inspired by key point prediction, sort of, it's not really massively dominating the other methods, but it's really doing very well and outperforming the best by a little bit. This is today the state of the art. And what's really fascinating is that there's no anchors there. So I spent all this time sort of motivating anchors as the traditional way to do things. And up until pretty much this year, anchors were the dominant way to do object detection. And it turns out just in the last few months, there have been a few papers that have leaked out, and they sort of do away with the whole anchors thing and directly predict a box. And they're doing surprisingly well. So I don't know where this is going to go. I don't actually think that anchors are bad yet, but this is definitely we're going to see a lot more papers that try to apply these kind of alternative ways of predicting bounding boxes in the future. Okay, all right, so that's it. I just want to recap. So I went through object detection. We talked about sliding window detectors. These are the dominant technologies still. So even if you're talking about ConvNets, they still use sliding windows in some sense. If you go to Google, Facebook, all of these companies use this style of model, right? I told you how to evaluate the detector in quite some detail, and I gave you a few practical tips and tricks for how to do this. We talked about semantic segmentation. The thing that I'm kind of most excited about is panoptic segmentation, which will let us combine these stuff categories with thing categories in a smart way. And then finally, we talked about key point prediction. And there's kind of two ways. So there's the top-down way, masked RCNN, and then there's also this competing bottom-up approach that, if you sort of follow your nose on the bottom-up approach, you get to this new anchor-free style of detection that happens to be really good. And that's it. Tomorrow I'll talk about, I'll go through some research vignettes, but that's it for today. Thanks.
good way of dealing with some computers. You see you're excited by it. Are there still open problems in that area, or like is that
Yeah.
haven't you taken kind of just the right approach? It sort of seems that way.
So we actually don't have, so the methods, if you look, they either do stuff or things, we separate them out. There's actually very few data sets that have both of these things labeled. And it's starting to, so COCO now has a panoptic segmentation track. And so some people have started doing this. My feeling, just looking at the winners from last year's challenge, everyone took their favorite semantic segmentation network, and then they took their favorite object detection network. They ran them separately, trained them separately, and then they sort of use some hacky way to put the results together. So that's the state of the art today. I see a few papers here and there that try to do this in a smarter way, but they're not kind of getting significantly superior results.
So you want to look at ways of avoiding kind of the classification, the stuff or things classification. Because if you do a hard one of those, then it does seem like it separates, right?
You want to avoid
avoiding making that decision?
No, so I guess what I would say is no, it's just kind of doing the two tasks jointly in a smart way, right? So things like mass.cnn, they produce a bunch of overlapping instances. So this is fundamentally kind of incompatible with semantic segmentation. And so in the panoptic segmentation world, you're sort of in a place where you're forced to make a decision about what a pixel, which instance a pixel needs to belong to. Instance segmentation doesn't have that constraint. So it's a slightly different problem compared to either instance segmentation or semantic segmentation. There's also the kind of idea that bringing them together is beneficial. So if I know that I'm on if this pixel is in the middle of a sandbar, maybe it's a child having fun. I don't know. Right?
Questions? Just curious, what would be your advice for people working in this field? Because it seems research in all these fields goes very well. Things will actually what would be your advice or tips to be aware of what is going on in this community?
Yeah, it's really hard. I don't know. I don't know if I have good advice. Read a lot of papers. Yeah, and I think that not trying to. I think it's important to not try to do everything. So there's a lot of cool problems, and I have colleagues always working on a really, really cool problem that's kind of similar to a problem that I'm working on. And there's always this kind of gravity, I should kind of be jumping onto this bandwagon. And sometimes I do, but I don't think it's always a good idea.
There's a question about the last part. I did that from extension of approach to the idea of the video. When you take into account
It's a question whether there are methods that do that? Yeah. So I'm less familiar with that literature, but I mean, I know people work on key point tracking, so you might want to also learn an embedding. I need to embed my left hand so that at time t+1, I can identify that with the same left hand in the next frame or something.
more questions? So, no more questions. We'll do a 5 to 10 minute break. Coffee break.
Thank you. Thank you for your help. Gracias.
I'll give it back to you tomorrow.
Oh, yeah. Otherwise, I'll go back. I know.
Yeah, for that.